Hi, welcome back to Unit 4, Linear Momentum here in AP Physics C. This is topic 4.2. This is change in momentum and impulse. And so this is not much different than last year. The idea is the same, but what we're going to do is we're going to bring in a little bit more calculus into this, okay? So the rate of change of a system's momentum is equal to the net external force exerted on that object or that system. So F net is equal to dp dt. And the way you think about it, this is a rewriting of Newton's second law, right? So this is relating momentum to Newton's second law, okay? Now, impulse, all right, so this idea of exerting a force over a time, okay? This is, we're going to use calculus here to find it. So if you look off to the right here, we have a crash test data. Their computers will find, the area under this curve here. And that is going to be given to us as the impulse. Now, I may be jumping ahead here because we may talk about that in a little bit later, but that's very important for car safety. So impulse is simply is defined as the integral of a force exerted on an object or system over a time interval. So J is equal to F of t dt. Now, this is for a variable force. If the force is constant, J is just simply F delta t, okay? So again, like the difference between physics 1 and physics C is the force variable or is it constant? If it's constant, it's the stuff from physics 1. If it's variable, it's the stuff from physics C. So impulse is a vector quantity, has the same direction as the net force exerted on the system. So if I'm exerting a force to the right, that means my impulse is also going to the right. Impulse is the important thing when it comes to car safety. So airbags, right? The goal of airbags is not to change the impulse. The goal of the airbags is to extend the time, right? So we're increasing delta t, which because of the inverse relationship then will decrease F. Right? Because J will stay the same, right? And the next statement, right? So change in momentum is the difference between a system's final momentum and its initial momentum. So delta P is P final minus P initial, right? Again, note that momentum has a vector field to it, okay? And then finally, we get to this point where we know as the impulse momentum theorem, okay, it relates the impulse delivered to an object and the change in that object's momentum. And so we write it as J equals the change in momentum. And what they'll try to do on a multiple choice question is say, okay, impulse equals, and two of the answer choices will be momentum and change in momentum. So sometimes what happens is, typically that initial momentum is zero or one of the momentums may be zero. And then, we just write it as J equals P final or P initial. But knowing that P final, P initial is actually a change in momentum, okay? And then if we want to expand this out, right? So the integral of F of t dt is equal to, right, M delta V, okay? And again, so the area under a force versus time graph, right? This is the impulse given, but it's also the change in momentum, right? So the change in P. All right, so let's look at an example problem. So we're given that a net force acting on an object moves in a straight line. It's given by the function of time t by F of t equals kappa t squared plus tau, where kappa is 2 newtons per second squared, tau is 4 newtons. What is the change in momentum of the object from 0 to 3 seconds? Okay, well, this is this idea of they're giving you information for an impulse, but they're asking you for change in momentum, right? But the good thing is, remember, impulse equals change in momentum. So what does that mean? The integral of F delta t, right, from 0 to 3 seconds, or sorry, I wrote F delta t, but we want F of t So f of t dt, okay, from 0 to 3 seconds. That'll give us our change in momentum. So that'd be like if I took this function, put it on a graph, the area under said graph is what we're looking for. Okay, and so we get the integral from 0 to 3, and I'm going to plug in the numbers, so I'm going to have 2t squared plus 4 dt. So that 2t squared, that is my force, and then I'm going to integrate it from 0 to 3 seconds. Okay, and so we follow our rules, all right? It's n plus 1, sorry, excuse me, x to the n plus 1 over n plus 1. So this becomes 2/3 t cubed plus 4t. And we need to evaluate that from 0 to 3 seconds. So what does that mean? That means we have a graph that looks, something like this. And we want to find, from this point to this point, what is the area under this curve? Okay. And so we just plug in our numbers. So we have 0, 2/3 times 3 cubed plus 4 times 3. And that's our first part, minus 2/3 times 0 cubed plus 4 times 0. The good thing, as long as that last part has the variable, we know that the last part is just going to be equal to 0. So this is just going to be 0, and our answer is going to lie right here in that first section. And so you plug into your calculator, and you find that the change in momentum for this object is going to be 59 Newton meters. Okay. So that was the impulse given to it. That was the change in momentum. There could be a part B to this section says, hey, what is the force experienced over this interval? Well, then you just simply, divide this by 3, and that would give you the average force. Okay. But this is the impulse momentum theorem. Now we're going to shift into conservation of momentum.